Now, surface waves are but one type of disturbance in the sun's outer layers. There's a wide class of dramatic and phenomena that occur on the sun, and they are caused by the sun's magnetic field. The first is sunspots. And they're just dark appearing regions. They range in size from a few hundred to a few thousand kilometers across. They last maybe a few days to maybe over a month. Now, in this picture, they look dark, which we might think they look cold. But it's not that they're cold, it's just a contrast. The surface of the sun where the granulation is about 6,000 degrees. The sunspot here is about 4,500 degrees. Now, that's still hot enough that if we had something 4,500 degrees, it would appear white hot to us. But it's not quite as bright, and so when we take a picture, we see a difference in contrast. And the reason it's cooler is that there's stronger magnetic fields inside the sunspots. Now here's a picture of the sun showing several sunspot groups. You can see how big these are. Over on the side here we have a picture of the Earth and how big it is. This sunspot group would fit several Earths inside of it. And the groups tend to go around the sun just like any other object on a surface of a rotating object. So why do we get sunspots? Charged particles tend to spiral along magnetic field lines easier than they drift across them. In other words, as I have some magnetic field lines here, it's very difficult for a charged particle to go through them. However, they can go along them relatively easily. So consequently, magnetic fields at the sun's surface slow the ascent of hot gases from below. So, starved from the heat below, the surface cools because it's in contact with space. Where the magnetic fields breach the surface, they create a dark sunspot. So I have magnetic field lines inside the sun, and where they come out, I get not as much heat flow, and so where it comes out and comes back in, I get sunspots. Now another object that we see on the surface of the sun that's due to magnetic field is something called a prominence. It's a huge glowing gas plume that juts from the lower chromosphere into the corona. You can see these pictures of these prominences as material spirals up and back down onto the surface of the sun. And it stays all together because it's trapped by magnetic field lines. And again, I have some pictures here that show you the size of this explosive material coming off the surface of the sun compared to the size of the Earth. So, the cool prominence gas is confined by its high magnetic field and hot surrounding gas. Gas streams through prominences in varieties of patterns, and they are associated with sunspots. Prominences tend to start and stop on a sunspot. Another object that we see is something called a solar flare. Sunspots are where solar flares occur. They're brief but very bright eruptions of hot gas in the chromosphere. This hot gas brightens over minutes or hours, not enough to affect the sun's total light output, but enough for us to see and shoot out a lot of material from the surface of the sun. There's a strong increase in radio and X-ray emissions during a flare. We have an intense twisting and breakage of magnetic field lines is thought to be the source of flares. In other words, as magnetic field lines come out and back in, sometimes they can get kinked, and as they kink and cross off, the explosion is this flare. Now, some flare eruptions can explosively shoot gas across the solar system, and actually, when there's solar flares, we know that a few days later we're going to have some very good auroral displays on all the planets, including the Earth. So the impact of a solar flare on the Earth is generally, as we see here, the northern lights. Now these solar flares can be very intense, and they can create enough of an effect here on Earth that they can actually cause blackouts. So, while the sun's magnetic field cools sunspots and prominences, it actually heats the chromosphere and corona. Heating is caused by magnetic waves generated in the relatively dense photosphere. The waves move up into the thinning atmospheric gases, they grow in magnitude, and they whip the charged particles back and forth to higher speeds and therefore higher temperatures. The origin of the waves may be from rising bubbles in the convection zone. So, as I have magnetic fields come out, you get this wave, and as that happens, as this wave gets larger and larger in amplitude, it causes the charged particles to move back and forth at higher and higher speeds. Higher speeds means higher temperature. Now we can measure the strength of a magnetic field due to something called the Zeeman effect. Magnetic field lines can split the spectral lines of an atom into 2, 3, or more components by changing the energy levels of the atom's electrons. Essentially, the electrons have something called spin, kind of like the Earth spins on its axis. And depending on whether the spin aligns, is perpendicular, or anti-aligns, I could get, instead of one spectral line where there's a magnetic field, I could get it to divide into 3. By looking at those spectral lines and how far apart they are and how many there are, we can determine the strength of the magnetic field. So the corona's high temperature gives its atoms enough energy to exceed escape velocity of the sun. Those atoms stream off into space and they form the solar wind, which is just a tenuous gas of hydrogen and helium that sweeps across the entire solar system. The amount of material lost from the sun via solar wind is really insignificant. In typical values at the Earth's orbit are a few atoms per cubic centimeter, and they're moving along at a fast rate of 500 kilometers per second. At some point, the solar wind eventually mingles with interstellar space and becomes part of the interstellar gas. Now, sunspot flare and prominence activity change yearly in a pattern called the solar cycle. Over the past 140 years or so, sunspots peak in number about every 11 years. And climate patterns on Earth may also follow solar cycle activity. So the sun undergoes differential rotation, which just means it rotates about 25 days to go around one time at the equator, and about 30 up towards the poles. Now, this rotation causes the sun's magnetic field to wind up, so it increases the solar activity. The magnetic fields essentially start off like the magnetic field from a bar magnet, but as the center of the Earth twists, it starts to twist the magnetic field lines, and as it does, we now get magnetic field lines in coils around the sun. Those coils can kink and break through the surface and cause sunspots. The cycle ends when the field twists too tightly and collapses, and then the process starts over and repeats. And that cycle can vary from anywhere from 6 to 16 years. On average, we said it's about 11 years. Now, if we also look at the polarity of the sunspots, the cycle is really 22 years, because each 11-year cycle, the polarity of sunspots, whether the north pole or the south pole of the field leads or lags, changes each cycle. So leading spots in one hemisphere have the same polarity, while in the other hemisphere they have opposite polarity. Now, we see then that there is some tie to weather, because if you look at Midwestern United States and Canada, they actually experience a 22-year drought cycle. Now, between 1645 and 1715, there was something called the Maunder Minimum. It happened about the same times as what they call the Little Ice Age in Europe and North America. Essentially, there were almost no sunspots during that time. We don't know why. The number of sunspots correlates very high with a change in ocean temperatures. Now, before we leave the sun, I want to review how we use its energy. Depending on what the cloud layer is and what our latitude is, we essentially get about 1 to 3 kilowatts of energy from the sun every square meter on the Earth. So lots of types of solar energy that we use. the first is, of course, just direct heating. You just put maybe some black pipes out, and we'll get hot water that way. We can use solar cells for electricity. Now, plants absorb sunlight, and they turn that into wood, or into fuel. Now, we can eat that, and we call it food, and that energy from the sun then is what keeps our bodies and animals' bodies going. We can burn it like wood and to heat up our homes or to roast marshmallows. We get fossil fuels from plants long ago that have died and have collapsed and have formed oil and coal. The sun also heats our atmosphere and causes it to move around, so wind power is actually a form of solar energy. Hydroelectric power is the sun evaporates water from the oceans, it goes over the land, it cools down and comes down as rain or snow. As it melts again, as it comes back down, we put a dam in its way and we generate power. Or there's another thing called OTEC, which is just the difference between the temperature up at the top of the ocean and the bottom, and using the temperature differential, we can actually generate electricity. The only types of non-solar energy we use would be nuclear energy, geothermal energy, which is stuff from the interior of the Earth, which is heated from the Earth's core and nuclear processes going in there, or tidal energy due to the changing of the tides from the moon.